Okay, let's go ahead and start. I'd first like to say hello and welcome everyone here tonight. I'm Regina Jorgensen. I'm the Director of Astronomy here at the Maria Mitchell Association, and I am very excited to be welcoming you all to our first Science Speaker Series talk of the summer season. And before we begin, I'd just like to make a note on how we will run tonight's program. First of all, I highly encourage you to ask questions using the Q&A function, which you should find at the bottom of your screen. And you can type in your question there, and we will have time at the end of the talk tonight to answer questions. So I strongly encourage you to ask any questions that you might have, and we will take questions at the end of the talk. And before we begin, I'd actually like to start by thanking our sponsors for tonight's event, who are Bank of America, Cape Air, and the White Elephant. And we really appreciate their support in helping us to bring you tonight's event. And also, as one final note, I'd just like to remind you to join us this summer every Wednesday at 7 p.m. here on Zoom to catch the latest MMA Science Speaker Series talk. So tonight, it is my great pleasure to introduce our speaker, Dr. Rudy Montez. Rudy is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, where he performs executive functions in the director's office of NASA's great observatory known as the Chandra X-ray Observatory. He's also a leading researcher in the field of nebulae that form as the result of stellar deaths, which is going to be the topic of his talk here tonight. Rudy earned his PhD from the Rochester Institute of Technology and held a postdoctoral fellowship at Vanderbilt University. And he's also been recognized numerous times, not only for his scientific contributions to the field, but for working and supporting and mentoring the next generation of diverse scientists. Rudy is the founder of the Latino Initiative Bridge program at the CFA, and he co-directs a program for undergraduates aimed at increasing diversity in astrophysics by supporting and mentoring undergraduate research students through crucial junctures in their careers. And Rudy is also an affiliated astronomer with the Maria Mitchell Association, where he teaches and mentors undergraduate research students in the NSF REU summer internship program. While many astronomical fields benefit from the ability to show pretty pictures in their field of interest, I suspect that Rudy might win the prize for the prettiest pictures of all. And you all are in for a real treat tonight, as Rudy will be sharing and explaining some of the most amazing and beautiful images that we have ever seen in astronomy. And most of them are the death remnants of stellar explosions, and he's going to tell us a bit about that tonight. So again, welcome everybody. If you have any questions during the talk, again, please feel free to type them into the Q&A, and we'll take all the questions at the end. And with that, I'd just like to say thank you so much, Rudy, for being here tonight and for taking the time to share all of your work and your research with us. And I'm very happy to welcome you, and I'll turn the floor over to you now.
Great. Thank you for having me. It's a pleasure to always visit Maria Mitchell and to visit the island. I enjoy it quite a bit. I'm going to try to share my screen now. Can you see my slides?
Yes, that looks good. And we see them in the correct view.
Okay. Before I start, real quick, I'm going to give you a little overview of what I'm going to talk about. I'm going to be talking about the end state of stars like our sun. And at the end of my talk, I hope you'll understand how we come to understand that stars are actually going to live a life and in that life, and also how we get so much information from these beautiful images that we see and look at. The title of my talk is Going Out in Style, How Sunlight Stars in Their Lives. And it's kind of a play on how beautiful these images are that we're seeing. And the image that we're looking at here in the background is called the Hubble Nebula. This is an image taken by the Hubble Space Telescope. And right there, can you see my cursor?
Yes, we can see it.
Thank you. right there in the center, that was once a star like our sun, maybe a little bit more massive than our sun, but very similar to our sun. And it's now just the core of that star. And all of the material that you see around is the material that was once a part of that star like our sun. And it's now been thrown into space. And you can actually see there's like cometary-like objects all around this rim here that are essentially just the intense radiation from that core here, just irradiating that material and creating these trailing shadows behind it. Really exquisite detail. By the way, this is one of the larger planetary nebula that is in the night sky. Larger because it's closer. For the most part, these planetary nebula all go through certain sizes, evolve through a certain size, but they're all at different distances. So some of them look smaller than others when they could actually be the same physical size, but it's just because they're further away that they appear smaller. This is called the Spirograph Nebula. If any of you have ever played with the spirograph, then you know what this is, but I know some people may not be playing with spirographs anymore, but you can see this wavy-like structure here, which it brings to mind a drawing you might do with a spirograph. And there again is that star in the center, which is actually the core of a star that's thrown its material into space. And you can also see there's a faint blue-like second inner nebula inside of there, and we'll talk about that more later. Here's another example called the Blinking Nebula. Again, it has this central shell of gas, and then you have this extra gas out here. And you have additional features shown here and here. This is called the Blinking Nebula because that star in the center is so bright that if you look at this nebula through a telescope, the star appears to actually blink in and out, but it's not actually varying. It's just a trick of your eye because the star is so bright that sometimes your cones can see it and are trying to see it, and sometimes the rods of your eye are trying to see it. And it plays a trick with your eye where it makes it seem to blink in brightness. This is called the Eskimo Nebula. This is another nebula where you see that nice central star, and you see again this compact region in the center, and you see all of this material out here. And again, you see those cometary-like structures where the radiation from that central region is just blowing past all of that material out there and creating what we call ionization effects, or essentially just ultraviolet photons that are knocking atoms into excited states. This is a popular nebula that you can actually see really nicely with a backyard telescope or at the Loynes Observatory if they ever are looking at it. And there again is that star in the center. It's called the Ring Nebula because it has this ring-like shape. But when you look at this with your eye, it actually just has more of a grayish, greenish hue. It doesn't look as stunning as what we're seeing here, and that's because these images are created using a very specific process that I'll tell you about in a little bit. This one is called the Little Ghost Nebula. Again, you see the structure out here, but this one is actually much more, I would say the shell here is thicker than examples that we saw here, where you can see the thin layers of gas that are creating this structure that we see. This one seems more thick, a little bit more fluffy, we might say. And then it has some structure out here as well. And all of these structures are telling us something about how this nebula formed. This one is called the Hubble 5 Nebula, and it's what we refer to as a bipolar nebula. And that's because it has a lobe here and it has a lobe here. And the star is in there embedded in that central region, which is pretty dense. And so we don't actually get a good chance to see the star in the center there because there's a lot of gas and dust that could obscure it. This is particularly interesting because if you think about this shape, it's a bipolar lobe and it's oriented in space in this image. This particular one is oriented where we can see both of those lobes. But you could imagine that if it was oriented in such a way that we were looking down one of the lobes, if we were looking in this direction, we might see something that looked entirely different. And that's a problem that that plagues astronomers studying these objects, trying to figure out exactly what we're seeing, what the structure is that we're seeing. This is probably one of my favorite and most spectacular images that you probably are all familiar with. This is called the Butterfly Nebula. And you can see very nicely, it's one of these bipolar nebula. The star is right there in the center. You can barely make it out. We have a new paper that suggests that's actually not the central star, but just a star that happens to be passing by. And we think the actual star is obscured by this dark lane that you see, which is actually dust in that nebular region in the center. And all of this outflowing and wispy gas that you see out here, we followed up this object again with new observations, and we've actually seen that evolution in a time span of about 10 years. We've actually watched that gas expand away from the center. This is the new images that I was referring to of the Butterfly Nebula that we've acquired. And I want to real quick tell you a little bit about how we make these images like this. The way we do this is by actually looking at very small pass bands, we call them. So a small piece of the electromagnetic spectrum or a small piece of light. You could think about this as there's blue light, red light, and green light. We are looking at an even smaller pass band, smaller piece of light than that. And that we're looking at that small piece of light because it corresponds to a very particular atom. And the atom, when it gets excited, that atom will, electrons will rise to a higher level around that atom. And when they fall back, they emit a very particular photon at that very particular wavelength or that piece of light that we're looking at. In this case, in the red, we've color-coded the nitrogen-2 emission line. So this is nitrogen that has been ionized one time. So that means one electron has been popped off. And then when it collapses back down, it emits a particular photon. And in green, we've color-coded what's singly ionized hydrogen, so hydrogen gas that's been ionized once. And then in blue, we've color-coded iron, and this is again doubly singly ionized iron. So, and by color-coding these particular emission lines, we can see where these elements are in the nebula. So we can tell, for example, that here where you see there's a lot of blue, there's a lot of iron, and the iron is doing something very funny and interesting that we're trying to figure out as we speak. And then you can see that where you have orange is where you have a combination of these other pass bands, this nitrogen and hydrogen. And when you start to get red, that's where more nitrogen starts to appear. And then you can see there's a greenish hue towards the center where H alpha, or hydrogen gas, is dominating what we see. And that's the same nebula here, looking at it through different looking at different atoms and how they're actually emitting, so that we can figure out where that material is. This is probably my favorite image of all the ones I'm going to show you. And this is called the Cat's Eye Nebula. And it's one of my favorites because it's also the one that kind of laughs in our face about how much we don't know and how much we don't understand yet about how these stars and these nebula are forming and how these stars are dying. There you see in the center that core of the star, the remnant of the star, and then you see all of the gas around it. You see material here that seems to be flying out from the center. Here you see it on the opposite side as well. You see this spiral-like shape of gas. And in the center, you see this lobe-like structure. And then when you go out to the edge, you see all of these arc-like structures that seem to be more or less spherically symmetric. That is, they look like rings in the sky. And then you also see these striations or shadows that are blocking the light from that star going all across the image. There's so much information in this image, so much puzzle. And the main puzzle is, how do you go from something that at once appeared to be losing its material in a symmetric way, where that is, it's losing its material in all directions at the same amount. Maybe it's doing it in a episodic event, and that's why you see these different rings. where you have a period of high material being lost, a low period of loss, and then a higher period and a low, so on and so on. So these rings are actually helping us trace back the history of how that material left the star. So it starts spherically symmetric, and then something happens and it goes completely haywire with some structure, but completely different, not in this symmetric way, but in this point symmetric or asymmetric pattern that we see in this image. And we needed the Hubble Space Telescope to tell us this, because the Hubble Space Telescope is in space, so it doesn't have the problem of the atmosphere of our Earth. And the atmosphere of our Earth will actually blur these images through something we call seeing. The reason why stars twinkle is because the light from the star is actually being deflected by different molecules in our atmosphere, and that creates this twinkle-like effect. Twinkle-like effect when you're doing an image like this is just going to blur the image. And so you really need to go into space to see this fine detail that I'm talking about. Oops. So these objects are called planetary nebulae, and they actually have nothing to do with planets. The reason why we call them this is because when they were first discovered, if you looked at something in a primitive telescope, it might look like a blurry kind of structure. The point is that it has structure. It's not a point of light. The other things that had this structure that weren't points of light were planets. They look like a disk, so you can actually resolve them through a primitive telescope. And planets don't twinkle, and they don't twinkle because they actually have a size, whereas the stars are so far away, they're effectively just points of light. But they're not quite planets, they're a little fuzzy, and so they're called fuzzy planets or cloudy planets. And that's how the name Planetary Nebula came to be, and it's what we have kept since then, even though it's a little bit of a misnomer about what they actually mean. The other thing about Planetary Nebula is that, we see something that looks like this, and we might say that looks like a disk, so that looks like a flat object in space, but it's actually a shell, and that shell is being projected onto space, and it's a 3D shell. And so the material that we see on this side can be also in front of us, between us. And so it's kind of like an egg-like shape. If you took the egg of a shell and you put it into space, it's what you're looking at. Even though the shell has a certain thickness, you still see this part of the shell. And that's what we're seeing in all of these images here. 3D structure that's, again, flattened by our perspective, but not in actual reality. So the Cat's Eye Nebula is also really awesome because it's one of the I think hallmark planetary nebula that we know and think about. But one of the things that you may be wondering is, how do we actually know this story that I'm telling you, which is that this is the core of that star and all of this material is coming from that star? How do we know that a star, why is a star like this one over here in the upper left, why does that not look like this? But we can actually trace that, not in a human timescale, but we can measure that evolution by looking at a lot of stars at a lot of different ages. So to start this little tour, we're going to have a little interactive part in a moment. This is a plot of the sky of about 50,000 stars that are within 500 light years of the sun. This data is actually coming from the Hipparcos satellite, which is an older satellite. There's actually a new satellite that I had the Mariah Mitchell interns use this actually just a couple of days ago to actually do a similar study. I'm showing you here is what we astronomers call the right ascension. And so this is essentially, if you move around and you look essentially around the plane that we are on when we're here on the Earth, on the local plane of our location, goes from 0 to 360 degrees, and then the declination is essentially going up and down, and that's some of these declinations down here we can't see because they're blocked by the Earth, but we can always see the North Pole all the way up at 90 degrees, the North Star. So all of these stars I'm showing you here are, like I said, 50,000 stars that are within 500 light years. We can actually, I've color coded all of these by what astronomers call a color, that is how blue or how red the star is. And then I've also taken that information and how bright those stars are, and I put them onto this diagram here. So on this lower axis, this is blue, and this is a V color, so that's a green color. Blue stars tend to be hotter, red stars tend to be cooler. And so a star like Betelgeuse would be somewhere over here. It's very bright, and it's also very red. A star like Sirius would be somewhere over here. It's blue, and it's very bright as well. What I'm showing on this axis here is how bright that star is, to our perception. And so that means when you see something that's far away, it's going to get fainter, as opposed to if it was very close by, it would appear brighter. And so that's the observed magnitude or brightness of that star. And again, this is the color of all those stars that we saw on the previous plot. In order to actually correct that brightness of that star to something that's actually physically relevant to the star, we have to know how far those stars are so that we can scale them all, so that if they were at the same distance, we could say this one's brighter than that one. Not a perception thing, but an actual physical property of the stars. And to do that, we use something that I want you to now all practice at home. It might be hard for you to stand back from the screen, but if you hold your thumb up at arm's length, and you look at something in the distance of your room, and you close one eye, and then you close the other eye, close that eye that's open and open the other one. So blink back and forth between your two eyes, and you'll see that your thumb is actually appears to move against the background. I like to do this in person because I usually hear you all saying, oh yes, oh yeah, I noticed that, but I can't hear you all doing that. So I'm going to assume you're doing it. That actual apparent motion of your thumb is actually what's called trigonometric parallax, and it's a way to actually measure the distance to these stars. Instead of your eyes are separated by the distance between your eyes. What we actually do, astronomers, is we wait for the Earth to go in its orbit to the other side, and then we look at a nearby star, and it appears to be here. And then when we come to the other side of the Earth, we look at that same star, and now it appears to be over here. And that angle there, we can use to calculate how far away that star actually is to the sun. And we use that. It's called trigonometric parallax. It's what Hipparcos did for hundreds of thousands of stars, and it's what the Gaia spacecraft is doing for a lot more stars. And you may have seen some of the maps coming from that project, which are just phenomenal. It's a project run by the European Space Agency. So we can actually take all of these measurements that are the observed magnitudes, and we can calculate their distances, and then we can put them onto an actual physical brightness of those stars. And that's what I'm showing you here. I'll blink back. So you'll see that there's a spread here. And when we actually scale those with distances, we get a little bit of a tighter relationship, a thinner relationship. And that's where our sun would be in this diagram. This line of stars that you see going along here is what astronomers refer to as the main sequence. It's where most stars spend most of their lives. And chances are, if you're looking up at a star, it's on the main sequence. Down here, where you see a few stars, those are called white dwarfs. This is the end product. This is what we've been looking at in the center of planetary nebulae. And then over here, you have what we call evolved stars. These are stars that have left the main sequence and are now going through changes, and those changes are going to bring about the birth of the planetary nebula. This is the path that a star like our sun might take. It'll go through what's called the red giant phase. It'll go through, horizontal branch phase, and it'll go through an asymptotic giant branch phase, and then it'll shoot over. And this is when the planetary nebula is actually born. And the planetary nebula will last through this period here before it transitions down to a white dwarf. I have all of those labeled here. I don't expect you to read all of these. I'm just showing you them. I'll probably make the slides available to Mariah Mitchell if you are interested in reading more about this. But the lifetime of all of these phases vary quite a bit. So when you're on the main sequence, you're there for 10 to the 9 years. That's billions of years. When you're on this phase here where the number 1 is, you're there for about 10 million years. That may seem like a lot, but compared to a billion years, that's just a small time. And the time when you're actually forming the planetary nebula is the shortest time frame in all of these. So that planetary nebula for astronomers, to astronomers, is a very short-lived phase, actually. It's 10 to the 5 years, so that's about 10,000 years. Some of them will last for thousands of years. And that's why we can actually see them actually evolve in time. The other story here is about mass loss. So that main sequence star starts with a certain amount of mass. For a star mass like our sun, it's a 1 solar mass. And through these evolutionary phases, it actually loses that mass. It loses a lot of it here. And that's whenever you start to throw the material into space. And that's ultimately going to become the planetary nebula shells that we see. And that happens about later on, like I said. So we've been doing a lot of this with space telescopes, and it's really been amazing because they really show us these details that we haven't been able to see before. And so I'm just going to tell you a little bit about some of the other space telescopes that I've been using and we've been using to study these evolved stars. So I have 3 of NASA's 4 great observatories. The Great Observatory Program of NASA was this initiative that gave birth to the Hubble Space Telescope, gave birth to the Chandra X-ray Observatory, which is the telescope I work for, and the Spitzer Space Telescope, as well as the Compton Gamma Ray Explorer. Spitzer, all 3 of these were operating recently, but Spitzer is no longer operating. Hubble's been operating for about 35 years. Chandra has been operating for about 22, 23 years. And this again is where I work, the Chandra X-ray Observatory. So one of the great things that we've learned from Hubble's observations of these nebula is this variety of shapes. I mean, you see a lot of these elliptical-like shapes. I put these all into one scale for you, but then you see this nested shells that I mentioned before. You see some objects that don't have these nested shells. You see this asymmetry. You see material that seems to be sticking out from the rest of the nebular structure. Very few round and spherical planetary nebula, in fact. Most of them have some degree of asymmetry. These are those very extremely asymmetric objects. So this is a planetary nebula that looks almost like a square, but it's got some rounded corners here. This is one that's also elongated and has these streams of gas that seem to be left behind as that material is expanding. We saw the butterfly. This one just looks unreal. It's called the Hourglass Nebula. Looks like an hourglass, very nicely shaped, very nice shape, coherent structure. And again, the bipolar nebula that we saw before. So why are these so asymmetrical? And that's really the question that we've been trying to answer since we started getting these Hubble Space Telescope images. We tend to categorize these as round or elliptical, hourglass or bipolar, or even multipolar nebula like I'm showing you here. And the way that we think you get this is by taking clues from these bipolar planetary nebula, like I'm showing you up here, and like the Butterfly Nebula. You'll notice that in this image up here, there's 2 lobes and there's this pinched waist. So that seems to be pinched here. And then this gives rise to this classic hourglass bipolar shapes. But how do you actually form this? And one of the ideas that we have is that you maybe have a torus around that star. And so when that star starts to lose material, it's going to lose it preferentially in this direction and that direction because the torus or the donut-like shape is there to stop the material from going along the pinched waist direction. But then, so this is a schematic of how that might look. You have the star throwing material out. The material stops here, but it is allowed to progress in that direction freely. And that over time gives rise to this bipolar shape that we see in these nebula. This is a schematic view of what we think is happening there. But then the question is, where does this torus come from? So we've taken the problem of how do you shape these, and we've come up with a scenario, but now we have another question to answer for, which is, where does this torus come from? And a place that can very easily form a torus is around the binary system. And so this has given rise to what we call in the community the binary hypothesis. This is a hypothesis that most of these planetary nebula that look like this are probably coming from binary interactions. So you have two stars in there. Those two stars are orbiting each other. And as one of them starts to evolve and lose material, that material will shape this torus and build this torus, this reservoir of mass. And then when it starts to lose mass in a much more rapid and faster way, that's what will actually form the planetary nebula that we see later. So then that gives rise to an extension of that hypothesis, which is to say, maybe you can form all of the planetary nebula, not just these bipolar ones, but maybe you can form all of them through some kind of binary hypothesis, some kind of binary origin. And here's a little schematic I'm showing of how that might look. If your two stars start far apart, then you might end up just making something that's gently asymmetric, something like the Ring Nebula. If your stars start close together and they start to evolve, because that material is going out and some of it is going to be very close to the second star, you can form what's called a common envelope, where for a moment in time, those stars are both surrounded by a gas shell. And when they're in that gas shell, one of two things can happen. Those two stars can spiral into each other and then merge. And in that merger event, they could release a lot of material at once through some episodic explosive-like event. And that could form a nebula like this. Or those two stars will not spiral together, but they'll get closer and closer until they unbind that shell of gas, and that unbinding of that shell of gas could form a nebula with this nested-like structure that you see here. So we actually do have some clues for some of this binarity, some of this binary hypothesis. A lot of the work that I started with the Chandra X-ray Observatory is actually looking for evidence of these binaries. The reason why we have to go to Chandra is because although that star, well, the star in the center of all those nebula look really bright, and they are very bright. So any companion or binary of the second star in that system, we wouldn't be able to see because that star is so bright. But it so happens that you can see them in the X-rays. So what I'm showing you here are the clues from the Chandra X-ray Observatory that show us that there could be a binary there in the center. So again, here's the Cat's Eye Nebula, again taken with the Hubble Space Telescope. And then I'm going to show you now what it looks like in the X-rays with the Chandra X-ray Observatory. Well, I'll blink back and forth between those two. Oops. So you can see these are on the same scale. So this nebula and those X-rays are coming from the same size on your screen. Notice how here we have a lot of crisp structure, lots of nice detail. We don't have as much detail here in the X-rays, and that's because X-rays are very hard to focus. If you think about it, we use X-rays to see through our skin, to image our broken bones, or to get dental X-rays. That's because X-rays will usually penetrate softer material, and then they only get stopped by something hard. And they get stopped by something hard, not because they're deflected, but because they're usually depositing their energy into that harder substance. And so you can't make a mirror like you would for the Hubble Space Telescope. The mirror, like the Hubble Space Telescope, will not deflect or not reflect X-rays into a focus. They'll actually just deposit the energy into the mirror and that they won't be observed. What you actually have to do is what's called grazing incidence. It's a lot like skipping a rock on a pond. You throw the rock at a low angle, and when it hits the surface of the water, it skips. And that's essentially what we're doing with the X-ray photons. We take a mirror that's very flat, the X-rays come in and down, and then they deflect. And then you do that a couple of times, and then you get a nice focus image. Again, not as nice as the Hubble Space Telescope, but still pretty good, and the best that we've been able to do technologically yet, and for the foreseeable future. So what you actually notice here, here's a composite of those two, where I have the X-rays overlaid on the image. And what you see is a bright central source of X-rays. And that bright central source of X-rays surprised everyone. It shouldn't be there because the stars are not hot enough to create X-rays. And one thing that I later showed in 2010 is that if you have a binary system, the companion itself, because it's in this environment where it's going around the star in a very tight orbit, that companion gets what's called spun up. That means it generates a lot of magnetic activity, like the activity our sun has or will have in the coming solar cycle. And that generates sunspots, that generates coronal mass ejections, and all of those generate X-rays. And so we think now the X-rays from these point sources are likely coming from binary companions. And those binary companions are being revealed in the X-rays because that's where the companion actually outshines that white dwarf core that we saw before. Here's a survey that I co-led with my PhD advisor and an international group of astronomers of planetary nebulae. And here's 4 such planetary nebula. And here are the X-ray observations. You can see there's a bright point source in these and that one. This one, there is not a bright source in the middle. So its binarity cannot be revealed by X-rays. And here's the composite of those 4. So the last thing I want to tell you about is about the Spitzer Space Telescope. Just as a little caveat and aside, again, here's the X-rays from the Cat's Eye Nebula. Here's the Cat's Eye Nebula in the Hubble Space Telescope. And now I'm going to show you what it looks like with what it looked like with the Spitzer Space Telescope. Not very impressive. I think the X-rays are better than this. You'll remember X-rays, optical emission, so emission we can see with our eyes, and infrared emission, or essentially warmth and heat. We are all infrared emitters, which is a longer wavelength emission. This is the Spitzer Space Telescope's view of that nebula. You can kind of make out that stuff out here that we pointed out in the optical image. You can kind of make out the spiral structure there as well, but you don't get as crisp a focus here because you're trying to focus longer wavelengths, and that gives you a little bit blurrier image. You need a much larger mirror, something like the James Webb Space Telescope, to get a better focus. But if you take a step back, so once again, I'll show you this nebula here that we've been looking at this whole time, that we've been looking at in the optical. If you take a step back, that's the nebula there. And all out here, you can see traces and evidence of extra material that was a part of that whole mass loss process through time that we have been, for the most part, not paying attention to in this entire story, but it's all out there. It's all evidence of this history of material being lost by the star and forming these nebula that we see. And here it is again, but in the optical, a very deep image in the optical showing all of this gas external to the nebula that we've been looking at this whole time. You can see those shells there, showing some really wild structures that we're still piecing together. And I've shown here a little schematic showing you pretty much what you need in order to understand these nebula. And so what you actually need in the center, you have this very hot X-ray gas. So you need to go to very high energies or very short wavelengths. In order to study the nebula, you need to look at the near infrared and optical. And then to get all that material out there, you need to look at the dust and the molecules. That's where those are forming around this nebula. And you need all of that in order to form the full picture of planetary nebula and to understand them. And we're just starting to do that with the Chandra X-ray Observatory and these other space crafts I've mentioned. So here's the Hubble Space Telescope again. And here is here's the Helix Nebula with the Hubble Space Telescope. Here's the Helix Nebula with the Spitzer Space Telescope. Here's the Helix Nebula, again with the Spitzer, but with an extra pass, showing you a bright red spot in the middle, which is actually indicative of this debris disk. So something that could have been akin to our asteroid belt has been found around the Helix Nebula. And then finally, this is a composite of 3 satellites that I haven't even shown you, 2 of them, WISE and GALEX, showing you this structure that we've been looking at as the Helix Nebula, taking another step back and showing you that there's extra stuff out here that's only revealed in these other spacecraft. And you really need to use caution when you're studying these, because so much information can be overlooked if you're not looking at all of the light from these objects. So if you've been paying attention, I've told you that most of these planetary nebula are, maybe they're all coming from binary interactions. That may lead you to wonder, what about our sun? Our sun does not have a binary star. So is our sun going to make one of these beautiful objects that we've been looking at? And the answer is it still can. And the answer is because of Jupiter. The mass ratio between Jupiter and our sun is just enough so that when the sun starts to expand and lose all of this material into space, what Jupiter does is going to determine whether or not we form this exotic structure. So Jupiter could either drift outwards or it can drift inwards. And if it drifts inwards, it's going to spin stuff up. It's going to act like a binary star would act, and it's going to create some episodic events that could form a planetary nebula. So thank you for your time. I hope you've enjoyed that. I'm happy to take your questions.
Awesome. Thank you so much, Rudy. I can hear everybody out there applauding. And I'll just encourage, we have a couple questions already, but if anybody has a question, go ahead and pop it into the Q&A and we will take them. The first question that we have is actually, what are the sizes of the nebula that you've been showing?
That's a good question. Most of these, I'm going to say parsecs, and that's not going to mean anything to anybody. Most of these are less than 0.4 parsecs. And what is that in light years? Is it multiplied by 3?
3, yeah, yeah, exactly.
So that's about 1.2 light years. So the time it takes light to travel across these is about 2 years. So they're big by most standards, but not quite big enough. Our solar system fits inside of that. So the solar system definitely larger than the solar system. These nebula. I'm sorry if that helps answer your question.
Yeah, I think so. The next question, and this is going back to the early parts of your talk, is given all the elements are assigned by colors, is there a possibility that these colors may represent elements not known to us? And I think this was asked during the slide where you had the different H alpha and N2 color map of one of the nebula, the butterfly, I think.
That's a great question. Most of the the elements are formed from a number of protons and neutrons in the core of the atom, and how many that's pretty much going to determine the elements that we are aware of. And so most of that is already constrained by the physics, the atomic physics. And so we shouldn't find anything. We should not find any new elements because we understand how elements form. And so we shouldn't be able to find any new ones. But we do see lines in a nebula that we don't know what they are. And that's just because our atomic physics calculations haven't gotten to the precision to actually calculate all the possible emission lines that are coming from different atoms in different states. If you have a magnetic field, if you have a certain density of that gas, all of these properties change how the emission lines that we observe from these stars, how those atoms actually emit those photons. An interesting thing about one line in particular is there's a triply ionized oxygen line. We call it O3. And it's actually a forbidden line, which means that it doesn't happen in terrestrial conditions because it requires densities that are so low. And it only happens in these nebula that we see, or that's where we first detected that line. And then theoretical physicists showed that, okay, well, this is actually oxygen. For a long time, that was called nebelium because it was only in nebula. But then we realized that it was actually oxygen occurring in this state that we don't have on Earth.
Cool. We have another question from the earlier part of your talk, which is about the pinched waist, where you talked about the torus. And the question is, why is that pinched waist invisible? Yeah.
So it's not invisible per se. If I said that it's obscured, that means that we can't see into it. And we can see into it if we looked in the right wavelength. But in this image of the optical emission, it's actually, you can see there's a dark lane. There's a brownish like lane. That's actually dust. And that dust is blocking the light behind that dust. However, if you look at this in the radio, and we've actually done this, so if you use a radio telescope, you can actually map out that dust and gas, and we've actually done that, and we've done it for this particular object, and it's in our new paper that we released recently on this object with our new observations.
Awesome. I think you see a similar effect when you see the Milky Way in the sky at night. There's a lot of bright, but then there's also a lot of dark parts, and that's the dust obscuring the light from the stars that are behind the dust.
Right.
Okay, the next question is from Kat. Kat's wondering if you look at a bipolar outflow from the end instead of from the side, might it look like an elliptical one with a more dense area toward the middle? Like some of the differences in shape have more to do with what direction we're seeing them from.
Hi, Kat. That's an excellent question. It's right on the money. This object actually that I'm showing here, we're now starting to understand that this might be a bipolar-like structure that we're looking down the pole. And so we only see one side of the pole. And this could be all of the stuff that's in the equatorial region, or the stuff that we've been calling the pinched waist. And because of our perspective, we are seeing it in the form that we see, and the other lobe is on the other side of what we're seeing here. Similarly, this actually, the Helix Nebula, which we've always touted as one of the hallmark planetary nebulae, actually appears to have two lobes as well, and we're looking down them. And we do that because we get spectroscopy, and the spectroscopy helps us determine the expansion of the gas in the nebula. And by mapping that out, we can figure out the geometry of the nebula, but it takes a lot of observations to do it. So we haven't done it for all of them.
I think we have a question about that coming up, but I'm going to keep going here in order. We have a great question, which is how long does it take to form these shapes? Do some take longer than others?
Exactly. They do some take longer than others. It depends on how massive the star starts off as. If it's a more massive star, it actually makes the nebula in hundreds of years. And the nebula could actually go through its whole phase in thousands of years. If it's a lower mass star like our sun, then it'll take 10,000 to 30,000 years to make this nebula, ionize it, and show everything that we see from it. So they do change, they do vary by something that for you all may not seem like a long time, but for me, it's a pretty big stark difference between those two mass ranges.
Great. The next question is from Kathy. She says, wonderful talk. Thank you. You mentioned that the James Webb Space Telescope can provide better images at infrared wavelengths because of its larger mirror. Do you and your team have plans to use JWST for your research?
That's a great question. We do hope to. We submitted proposals for the first cycle. We did not get them, but somebody else did get some planetary nebula approved. One of the problems is that these are actually quite bright. And so some of them may not actually be observable by James Webb because they're too bright, but that's when we get this first cycle of data for the nebula that have been observed, we'll know better about what we can and can't do with James Webb Space Telescope.
Well, you're not the only one in the boat of having JWST proposals rejected. There are a lot of people in that same boat.
It was a hard call for proposals.
Yeah, everybody is excited about that telescope. Let's see, Jerry's wondering if you could advise NASA on what to do next to advance your line of research, what would be on your wish list?
That's a really good question and a bit of a loaded question if I answer it, but I'll answer it anyways. I would say a new X-ray telescope like the Chandra X-ray Observatory, a successor to that has improved technology. Like I mentioned, the Chandra Observatory was launched in, it's been operating for 23 years, and so it was launched in 1999. The technology had to get frozen in before that, and so the technology was already out of date when it was launched, but that's just a process for putting up these great observatories. You have to make sure it's ready to launch ahead of the launch schedule. We have improved the technology quite a bit. We've made better detectors. We've made new mirror materials, new mirror structures. We can make a better X-ray telescope now, a much better X-ray telescope. But Chandra is still great and is still doing awesome science, but it can't observe planetary nebula as much anymore because over time the spacecraft has been the detectors that we use have been contaminated by material. It's probably stuff from the spacecraft itself because the spacecraft was originally designed to be run for 5 years and it's now been 22, 23 years. And so it's actually starting to show some age. And one of the things that happens is plasmas that I study. So those in planetary nebula, they're cool by conventional standards. They're not that hot. They're about 1 million degrees. Those plasmas are harder to detect because of the contaminant on the detectors. However, 10 to the 7 or 10 million degree plasmas, those are just fine. They're not harmed by this contaminant, so you can still do all of that science. It's just the science that I do that I can't do anymore. I can do it, it just takes a lot more time, and when time is the most valuable asset, it's hard to convince a committee to give you that time. Even if I do work for the spacecraft.
Great. We have a couple more questions. Kathy has another question, which is, you showed spectacular images of the material surrounding some of the nebulae that is located at very large distances away. Are you able to measure the chemical composition of such material or perhaps other properties like the kinematics of the material? And if so, does it help you learn anything about how the interstellar medium gets enriched by dying stars?
Absolutely, definitely, great question. Some of the really cool things that we can do is with integral field units. These are actually detectors that each pixel in the image is actually a spectrum, and those allow us to map out the abundances of the material. So how much iron, how much carbon, how much nitrogen. They also allow us to map out the kinematics across the nebula, and this is how we can infer this three-dimensional information. And all of those things help us understand the progenitor of the nebula, so what the initial star was. And it helps us, most importantly, calculate that initial to final mass ratio. And that's really the question that we need to say how these stars actually fill the ISM or populate the material between the stars. It's going to take some time for a star like this Helix Nebula for that material to get recycled through the ISM. It's not as energetic and not as large of a mass loss as in the supernova explosions, where that material is just flying out into the ISM and actually shaping and pushing out the ISM. But this material does end up around there. And it gets processed, and you make molecules out in that outskirts of that nebula. You make molecules, those molecules go into the ISM and go to be the reservoirs for the next generation of stars.
Great. We have two more questions. The next question is from the astro interns, and they're wondering, in the zoomed out Spitzer images, was the material that is spread out, so I think they're talking about the very outside material, ejected at the end of the star's life during the planetary nebula phase, or was it shed earlier during the star's life?
Most likely earlier. So all this material came earlier in the formation. And that's because it's a very slow moving material. The velocities that we do have for any of this material are order of magnitude lower than what we see in the velocities here. So okay, this material can catch up to this. The material in the center will eventually catch up to this material, but it hasn't done it yet.
And the last question is actually a great follow-up to that, which is Maya's wondering, how did the nebulae end now? So what is what's the future? Mm-hmm. What is the end of these nebulae going to look like?
That's a great question. The star in the middle, that core of the star, which is very hot, that is providing the ionizing photons that's illuminating all of the gas that we see. That star is fading. It's taken a long time to fade, but it is fading. Eventually it'll fade so much that it will no longer be able to illuminate that nebula, and we won't see the nebula anymore. The gas will still be there, but we won't see it in this beautiful display.
What is the rough timescale for that process?
That's about the 10,000 to 30,000 years.
Okay. Great. I think my questions were actually already asked by others tonight. I was just looking at my notes, but I think they've actually already been asked by others. So last call, if anyone has a last question, pop it in the Q&A. And while we're waiting to see, I will just really quickly thank our sponsors again, who are Bank of America, Cape Air, and the White Elephant, who sponsored tonight's event. And I'd like to remind everybody to be back, same place, same time, Wednesday at 7 p.m. throughout the summer to see an array of other astronomy and natural science talks that we'll have for you this summer. Oh, I do see one more question in the Q&A. Oh, it's a thank you. Thank you, great talk. And oh, we do have one more final question, if you're okay taking one more question, Rudy, which is briefly explain the origin of the jets of the nebulae. I think you had a couple nice examples where, yeah, in fact, this one that you're showing where you kind of see the jets. What is the origin of those jets?
The short answer is we don't know. The longer answer is that it could be related to the binarity of that central star. When you have those two stars orbiting each other, spinning up magnetic fields, you could actually launch material outwards in outflows that are collimated into what we call a jet.
Awesome. Okay, well, thank you so much, Rudy. This was fantastic. And these images are just really astounding. And the work that you've done is fantastic as well. And I'd like to thank you so much for taking the time to share it with all of us tonight. And we really appreciate everything that you're doing for the Maria Mitchell Association as well. And thank you to everybody who's attended tonight's talk. And if you did miss the talk, part of the talk, or you want to share it with your friends, we will be posting the recording from tonight's talk on the Maria Mitchell Association YouTube channel. So you can look out for it there and rewatch it or share it with anyone that you like.
Thank you for all your questions, and thank you for having me again.
Yeah, and we're getting lots of thanks from the audience. So thank you all for being here tonight, and thanks again, Rudy.
Bye.
Bye-bye.